Okay guys, buckle up because today we're talking about 3x3 systems of linear equations. And these are our page turners, paper burners here. They're going to use a lot of space, so make sure you have plenty of paper ready in your notes. I'm going to be going over a lot of examples, 10 examples, which is like a lot. So this video might also be very long. The two most common algebraic methods when you do by hand are linear combination or elimination, substitution. Some people will use Cramer's rule on a 3x3. We will learn about that in the next lesson. Or matrices is probably the preferred one, which we will eventually learn. But here's essentially what we're doing when we do this by hand. So think about when we were solving our 2x2 systems. My goal was to take my two equations in two variables, eliminate one of my variables either through substitution or elimination, and get down to a 1x1 system, one equation, one variable. Okay, when we're dealing with a 3x3 system, we want to basically take our 3x3, knock it down to a 2x2 system, and then do elimination again. So we're going to be doing like a lot of eliminating here. So as our steps here, it says the first thing we'll want to do is identify the variable that will be easiest to eliminate twice. Treat my two new equations as a 2x2 system like we did before. And solve like we did before, so eliminate another variable. So once we get down to our first answer, and we're going to be writing our answer as something like called an ordered triple. So specifically if it's x, y, and z, instead of an ordered pair, it's an ordered triple. Then x, y, and z are written in that order. Once I find my first variable, say maybe I found y first, okay, in this particular system we're imagining, then I want to plug back into the 2x2 system. So if I know y, I should be able to find either z or x in the 2x2 system. And once I know both of those, I can plug 2 out of my 3 variables in to the original. So like it sounds like a lot of work, and it kind of is. Okay, and then lastly, substitute in our 2 known variables to find the final variable. Okay, let's try a couple examples. We're going to start with some really easy systems here. Okay, and we know this one's pretty easy because it's actually giving me one of the values right here, right? It's telling me z is 3. So I already know, as part of my answer, the z value in my order triple is going to be 3. So if I was writing this x, y, z, z is -3. Okay, well now I still need to find y and x. I guess we'll put labels underneath here. So I see in my next equation, well, if I substitute in z, so I put in -3 for z, we can quickly solve for y. Add 3 over, we get y is 5. Okay, so I now know z is -3, y is 5. We just need x. And in fact, the only equation that has x in it is the top one. So we're going to substitute in y. So plus y, which is 5, minus z, which is -3, equals 4. So minus a negative here will become plus a positive. 5 plus 3 is 8. Subtracting 8 over, we get -4. And dividing by 2, we get x is -2. Now, just like before in the 2x2 systems, these 3 values for x, y, and z should make all equations true. So if you plug that in for x, y, and z, all 3 equations have to be true. Okay, it can't just be true for 1 or 2 of them. It has to make all 3 equations true. And that's what we're finding. Okay, let's try another 3x3 system. And again, this is an easier case here for us because we can very quickly at least get one of our variables, right? So if we solve for y here, we should, dividing by -3, we find that y is -3. So we have one of our 2 values right away. So I don't know x, I do know y, and we don't know z yet. Okay, so how can I use that to help me? Well, my other 2 equations have all 3 variables. But I can use 3 to substitute in. That will kind of get rid of or eliminate the variable of y in both of them. So if I substitute in -5x plus y, since y is -3, I'm just writing, oops, no y there, but -3, minus 2z equals negative 28. Our second equation, I'm going to substitute in negative 3 for y. So 5 times negative 3 will make negative 15 minus z equals negative 11. Okay, so we're just substituted in for y in both of these. To make them look more like standard form, let's probably add this 3 over in that top equation, and let's add this 15 over in the bottom equation. This will look a little bit nicer for us. So we'll have, and I'll continue up here, 3x minus, oops, let's do the top equation first, sorry, negative 5x minus 2z equals negative 25, and 3x minus z equals 4. And so notice that we have a 2 by 2 system. We have 2 variables and 2 equations here. So let's say if I want to eliminate z, probably a good one to eliminate, I can multiply the bottom equation by negative 2. So that would give me a new equation of negative 6x plus 2z equals negative 8. Rewriting the top equation, just bringing it down here so that they're all lined up. Now we can do elimination on our 2 by 2 system. So my z's will cancel. I get negative 11x equals negative 33. And I like that we're going to get a nice answer here. Dividing by negative 11, we get x equals positive 3. Now remember that these values should make either equation true. So to get z, I need to plug back into one of these 2 equations that has z. I'm going to choose the second equation. I think those numbers look a little easier to me. So we'll use green down here. 3 times x, which is 3, plus 5 times y, which is negative 3, minus z equals negative 11. So this becomes 9 and negative 15. 9 minus 15 is negative 4. Sorry, negative 6 minus z equals negative 11. Add 6 over, we would get negative z equals, adding 6 over, sorry, negative 5. And dividing by negative 1, we get z equals 5. So I've got x, I've got y, I've got z. Put in my 5 over there. As you can tell, this was somewhat of an easier system, but it still took quite a bit of work to get to our 2 solutions here. Okay, and we do write them as these ordered triples. So this is how you would write your solution with x, y, and z. Okay, here's our next equation. And the first thing we're going to try to do is figure out which variable would be the best to eliminate to create that 2 by 2 system we want. And I notice right away that one of my equations doesn't have all 3 variables. In fact, this equation at the bottom, which you can call equation 3, only has x and z. So if I can create another equation that just has x and z, I'll have my 2 by 2 system. So I think that gives me the idea that I want to eliminate y. If I can combine these top 2 equations and eliminate y, I'll get a second equation with x and z, and we'll have our 2 by 2 system. So let's figure out how to cancel out y or eliminate y. I think we can make those meet at 15, but that's going to require me to multiply the top equation by 3 and the bottom equation by 5. Okay, so let's write our 2 new equations. I'll do that over at the right here. This gives me 18x minus 15y plus 3z equals negative 75. Just remember to multiply both sides by 3. Multiplying by 5, we get 10x plus 15y plus 10z equals negative 35. And again, our goal was to combine these in such a way to get rid of y. So my y's will cancel. And I get 28x plus 13z equals negative 110. Some pretty ugly numbers here. But it's important to realize that I now have, if I use my third equation, this guy here, I now have a system that has x and z twice. This is a 2 by 2 system like we solved in the previous lesson. So I could do elimination. If I'm doing elimination here, maybe I want to multiply the bottom equation by negative 13. If I want to get rid of z. Oops, both sides here. So doing that, that would give me negative 13x minus 13z. And negative 13 and negative 5 is positive 80. So I'm going to write the other equation, this one. Just bring it over here so they're nice and lined up to add them together. So we add up. Now we're solving our 2 by 2 system here. The z's cancel. We get positive, was that 14? No, sorry, 15x equals, and then over here we end up with negative 30. Ooh, we're going to get a relatively nice answer. X is negative 2. That feels good when you get a nice whole number answer, right? If I made a bunch of calculation mistakes, it probably didn't divide nicely at the end there. Okay, so for my solution, we've got negative 2 for x. I don't know y or z yet, but we're coming for them. All right, so to find y, this is the important part. You can substitute in to any of your new equations as well, like the 2 by 2 system. So in fact, sorry, we're not solving for y yet. We need to solve for z first. And I like the one in blue. X plus z, so negative 2 plus z equals negative 5. I can solve for z pretty quickly here. Add 2 over, I get z is negative 3. So we've got our answer for z, negative 3. Now to find our answer for y, we need to plug back into one of the two equations with y, either the top equation or the one in the middle. I kind of like the smaller numbers of the one in the middle, so I'm going to use the middle equation here. 2 times x, which is negative 2, plus 3 times y, which we don't know yet, plus 2 times z, which is negative 3, should equal negative 7. So multiplying, we get negative 4 plus 3y minus 6 equals negative 7. These two together make negative 10. Adding that 10 over, we get 3 equals negative 3. And dividing by negative 3, we get y is negative 1. So look at all this work. I know I kind of crammed it all up in here because I've got another problem we're going to fit on this slide. But there it is. All of that work. We found our 3 values that should make all 3 equations true. Okay, here's one for you to try out that's very similar to what we did in example 3. So this would be a good time to pause the video, try this out, and if you're stuck, the answer will be up here. All right, how'd you do? If you came up with 0, negative 3, and negative 1, awesome job. So just to run you through what I did super fast here, I noticed that one of my equations only had x and y, so I wanted to have another equation with just x and y to get a 2 by 2 system. So that immediately told me I wanted to eliminate z. And I know I could make these meet at positive 4 and negative 4z. But that would require me to multiply the second equation by 4. So there's my new equation. I combined it with the one up top and canceled my z's out. That gave me the equation in green here. Okay, so then I use that and the existing equation with x and y as my 2 by 2 system. And looking at, I either had to make these meet at 22 or make these meet at 3. And making those meet at 3 was better for me. So I multiplied the top equation by negative 3. That's what I got here in red. Then I combined it with basically the equation we started with way back here. We canceled out our y's. We got 31x equals 0, which meant x was 0. Then I substituted back into this equation. But again, you could have actually used the equation in green. Any of the new equations you can plug back into as well. But plugging in 0 for x gave me 3 for y. And then I went to the top equation to substitute in x and y and solve for z. All right, here is an example where we have all 3 equations with all 3 variables. So it doesn't give me a direction as to which variable or which 2x2 system I want to try to solve first. So what we want to look at is our coefficients to see what would be the easiest to eliminate. I could make all three of these maybe meet at 6. That wouldn't be a bad choice, 6 and negative 6. I could make these all meet at probably 6 as well, where I would just need to change 2 of the equations. And here I could make these meet at 6, or, ooh, I like that even these z's would cancel each other out as is, so that's pretty nice. So I'm thinking z might be the better method here. So there is some notation that I didn't use on the other ones that sometimes people will use, so you can kind of keep track of their work. So I'm going to label these equation 1, equation 2, and equation 3. And the very first thing we're going to do here is we're going to take equation 2, which is x plus y minus 2z equals 18, and we're going to add it to equation 3. So I'm just going to rewrite equation 3. This is where I saw my x's, whoops, minus 3y. This is where I saw my x's would cancel out, equals 7. Or sorry, not x's, z's, where my z's would cancel each other out. So we're going to add equation 2 and equation 3 together. And this is just notation. We're not actually adding numbers there. And I end up with 7x, let's do this in a different color, 7x minus 2y equals 25. My z's canceled out. Okay, so here's my first equation in my 2x2 system. Okay, so now I want a second equation that just relates x and y. So I need to eliminate z again. I kind of like the second equation and the first equation. The second equation over the third because it's already the opposite sign here. So I'm going to rewrite the first equation, x plus 6y plus 6z equals 11. And we're going to take the second equation, and this is how you do the notation here, the second equation, but we're going to multiply everything by 3. So rather than writing times 3 over here, I'm just using the notation to say this is the second equation with everything multiplied by 3, which would give me 3x plus 3y minus 6z, and the 18 times 3 is 54. Okay, and then we're going to add these together. Okay, again, this is all just notation of what we're doing. We're not actually adding those numbers together. X and 3x give me 4x. 6y and 3y make 9y. My z's cancel out. And 11 and 54 make 65. Okay, so in green, I have my two equations for my 2x2 system. So maybe I'll copy my 7x minus 2y equals 25 here, just so they're above and below each other. But this is the 2x2 system I need to solve. So my x's will either meet at 28 or my y's will meet at 18. Let's make the y's meet at 18. Seems like probably a better choice here. So we need to multiply this new equation by 2. So that would give me, and I'll try to find some room over here, 8x plus 18y equals 130. Okay, my second equation here, we would need to multiply by 9 to get that negative 18y. So 9 times 7 is 63x minus 18y, and 9 quarters is $2.25. Okay, so here's my 2x2 system set up to eliminate y. We can cancel this out, and we get 71x equals 355. 355. So let's hope this divides by 71. And would you look at that? We get exactly 5. Oh man, that feels good. Okay, we ran into a lot of big numbers there, but we found x is 5. So I can pick any of these green equations that were part of my 2x2. Since I know x, I can use one of them to solve for y. So maybe we'll use the 7 times x minus 2y equals 25. Excuse me, 35 minus 2y equals 25. Subtract 35 over gets us negative 10. And we end up with y equals 5 as well. So we got x equals 5, y equals 5. Now I need to pick any equation that has z in it. And I like this bottom equation. It looks pretty nice. Let's use this to find z. So 6 times x, which is 5, minus 3 times y, which is also 5, plus 2z equals 7. So this gives me 30 minus 15 plus 2z equals 7. 30 minus 15 is 15. Subtract that over to the other side. Gives us negative 8. Dividing by 2, we get z is negative 4. Look at all that work. All of that work, but we finally got our answer. X is 5, y is 5, z is negative 4. Okay, here's one for you to try out. I know that was a lot of work to do, but try it. The struggle is part of learning. Try this one out, pause the video, see how far you can get, and then check. All right, let's see how you did. You got negative 5, 1, negative 1. Great job. I made a bunch of sign mistakes I had to go back and fix here. If you're getting some ugly numbers that aren't dividing, notice once I got way over here, I had to divide 265 and negative 53. If it's not coming out to a nice whole number, I wouldn't be mean enough to give you fractions to plug back in on these by hand. So you should be getting integer answers, like positive or negative whole numbers. So when you're trying to divide, if you're not getting one of those, go back and check your work. But here's what I did. I decided to cancel out z's. So I did 6 times equation 1 and added it to equation 2. Okay, that gave me this result in green. Then I decided to cancel out z's between 1 and 3 by just doubling equation 1. So 2 times equation 1, added it with equation 3, got my second equation in green. Then I brought this one over and set up my 2 by 2 system. Unfortunately, these did not meet at a very nice low number. I chose to make 8 and 15 meet at 8 times 15, or 120. So we got some very big values here, but luckily, again, it did divide nice when we got negative 5. Okay, then I plugged into the first equation I got in my 2 by 2 system, plugged in my x value to solve for y, and then used x and y in the first equation to solve for z. Again, you could choose any of those 3. Okay, so here is a system where we can see we're missing some of the variables, which is nice. And I probably want to try to combine, say, maybe these first 2 equations right away. So if we were to try that, and I go to call this equation 1 and equation 2 up top, and we went to add those together. 4x plus 6y equals negative 12, and negative 4x minus 6y equals positive 12. I'd hope we see just combining those already that my x's and y's cancel out, and I get 0 equals 0. So this is, again, kind of one of those special cases where we're either going to get infinitely many solutions or no solution. And in this case, because what these really mean, if you're graphing something like this with 3 variables, that we're basically graphing in 3 dimensions. These are planes, like flat surfaces in 3-dimensional space. So we're looking for the intersection of 3 planes. And when we get that one exact solution, that means that they are intersecting in one single point. Okay. In this case, for our particular one, we've got this one line of intersection. So there's an infinite number of solutions, but they end up being on this line. So this is infinitely many solutions. All right, when we get this true statement, infinitely many solutions. Okay, let's check out our next problem. Okay, in my next problem, looking at my equation here, I would probably say y looks like the nicest to eliminate here. So let's try to get rid of y. So I can do my first equation times negative 1. So negative 1 times the first equation gives me positive 6x plus 3y plus 6z equals 24. Equals negative 24. And then I can just add my second equation, which is negative 4x minus 3y minus 5z equals negative 27. Okay, so we've set this up so that my y's cancel out, and I get 2x plus z equals negative 51. Okay, so I want to have another equation with just x and z, so I want to eliminate y again. So I've already done 1 and 2 together. I could do 1 and 3 or 2 and 3. Let's say we do 2 and 3. So 2 and 3 over here. Sorry, I know you can't see that writing. It's going underneath it. So we're going to do equation 2, just as is. Negative 4x minus 3y minus 5z equals negative 27. And then we're going to multiply equation 3 by 3. So 3 times equation 3 gives us negative 12x plus 3y minus 3z equals 54. Okay, and then adding these up, we get negative 16x, my y's cancel, minus 8z equals 27. Okay, so here's my 2 by 2 system. I can bring the one over in blue a little closer just to closer examine it. 2x plus z equals negative 51. So let's say I want to make my x's cancel out. Well, I can multiply the bottom equation by, say, negative 8. Right, so that would give me negative 16x minus 8z equals 408. Okay, the top equation, which is still in green, I'll just bring down negative 16x minus 8z equals 27. And we'll go to add these guys together, and my x's cancel, and uh-oh, so do my z's. So I get 0 equals 435. Well, that is definitely a false statement. What that means is there is no solution. Okay, and in this case, no solution, the visual representation of these planes in space, you could have parallel planes. There's lots of different visualizations here. You could have parallel planes. This is kind of an intersection of all three planes where we got one single solution in three-dimensional space. And then here are three different ways that we could get no solution, where these planes don't all intersect in one singular point. Okay, you don't have to worry about the graphical representation too much, but just an idea of what that would look like. All right, we've got a couple word problems here. The toughest part about these word problems is really setting up the three equations when we have three unknowns. So I'll help you set up the equations here, and then I will just put up the solutions. If you want me to go over these specifically, how to solve them, we can do that in class. But let's try to set these up. The University of Michigan and the University of Tennessee scored a total of 62 points during the 2002 Florida Citrus Bowl. There were 18 different scoring plays, which were a combination of touchdowns, extra points, and field goals, worth 6, 1, and 3 points respectively. The same number of extra points and touchdowns were scored. How many touchdowns, extra points, and field goals were scored? So right here, I automatically see we've got three different unknowns to solve for. So let's define some variables here. Let's let x represent the number of touchdowns scored. Let's let y represent the number of field goals scored. I'm just going by points, I guess top to bottom. And let's let z represent the number of extra points scored. Okay, and again, clearly define your variables. That helps you set up equations. So let's see what relationships we have between these where we can set some stuff up. I know that there were 18 different scoring plays. So that means however many touchdowns, field goals, and extra points, I'm not sure how many they made of each, but I know that adding them together, the number of touchdowns scored plus the number of field goals scored plus the number of extra points scored, all together has to equal 18 scoring plays. So there's my first equation. Next, it's talking about points, so maybe some point totals will help us out here. Let's see. I get 6 points for every touchdown scored. I get 3 points for every field goal scored. And I get 1 point for every extra point scored. And it told me together there were 62 total points scored. Okay, so we set up an equation that has to do with points scored. So I still need a third equation, and it gives me a little extra information down here. The same number of extra points and touchdowns were scored. So extra points and touchdowns were the same. That means, mathematically, that means they're equal. That x is equal to z. That x and z are equal. Now, if I want to put these on the same side, right, I could move the z over and say x minus z equals 0. Right? If they're the same number, they should equal 0. So if you wanted to do something like this to set it up like our other equations we were working with, that's fine. But hopefully this gives you an idea that maybe canceling y, right, because I already have an equation with x and z, would be a good idea to solve this. Okay, so that's set up. If you want, you can go through and pause and solve that now. I'm going to go ahead and set up the second one, and then I'll put up the answers at the end. Okay, but there's our 3x3 system. A couple things we should note, though, when we talk about these word problems. For these ones, you can't score half of a touchdown or 2/3 of a touchdown, so we should be getting positive integer answers, or at least non-negative integers, right? Maybe you scored 0 touchdowns, but you can't score negative touchdowns or fraction touchdowns, etc. So number 10, the UNLV Rebels basketball team scored 90 points, we're talking about points again, from a combination of 3-pointers, 2-pointers, and 1-point baskets. They made 51 baskets in total, and there were 11 times as many 2-point baskets as there were 3-point baskets. Ooh, that seems confusing. How many of each type of shot were made? Well, again, we need to define our variables. Okay, so I've defined my 3 variables. I let x be the 3-pointers, y be the 2-pointers, z be the 1-pointers. Again, number of each type of basket made. So again, we have one where it's talking about the total points. So let's set up an equation that has to do with points. So I know I get 3 points for every 3-point basket made, 2 points for every 2-point basket made, and 1 point for every 1-point basket made, aka free throws. And I know together, those total number of points need to equal 90 points. It also told me about the total number of baskets that were made. 51 total baskets. The number of 3s, the number of 2s, and the number of 1s together has to equal 51 total made baskets. So we've got 2 of our 3 equations. And it's this last one that could be pretty tricky to set up. There were 11 times as many 2-point baskets as there were 3-point baskets. So we're doing a comparison between 3-point baskets and 2-point baskets, between x and y here. So if you read this, which value is going to be bigger? Right? We scored 11 times as many 2s as we did 3s. So that tells me we scored a lot more 2s than 3s, right? So this is definitely the bigger value. So when we go to set up the inequality here, or equation, in order for these to be equal, right, I would need to take the smaller value, which in this case is x, and multiply it by 11. That way, the number of 2-point baskets is 11 times as many 3-point baskets. Hopefully that makes sense. The number of 2-point baskets is equal to 11 times the number of 3-point baskets, right? So here's my equation. If you want to move y over to set it equal to 0, so we can kind of align this up like we did some of our previous equations, you can do that to help you set up and solve your system. Sorry, 11x over there minus y equals 0. And again, I would probably eliminate z in the top 2 equations to get your second equation with x and y. But go ahead and try those out. I'm just going to put up the final answers. If you want me to go through these in class, I will be happy to. So pause now, give these a try. Right, here are our results. For the top one, you should come up with 8 touchdowns, 2 field goals, and 8 extra points. Down below, the Rebels scored 3 threes, 33 2-point baskets, and got to the line and hit 15 free throws. Again, if you didn't get these and you want me to go over solving of the equations, please ask me in class. We'll do some more word problems and some more systems.